Welcome back to Stack Lessons. In this lesson we're tackling Senior Engineer Walkthrough, 15 real-world scenarios, one of the trickier topics on the exam. Let's break it down. By the end of this video, you'll have a repeatable habit for making 15 of the most common Databricks GenAI architecture calls: chain versus agent, endpoint shape, where to put masking, which scorer to reach for. We're sitting next to Data Dino's senior architect for a normal Monday sprint, watching her read each ticket, eliminate the options that won't survive production, and pick the Databricks-native primitive. The same instinct works on scenario questions in the certification, but the real prize is the production decision intuition. Episode 20 took us through 10 production decisions using one habit: read the scenario for the binding constraint, eliminate what violates it, prefer the Databricks-native primitive. The instinct doesn't change. By now you've seen the full stack: vector search, the agent framework, PyFunk, MCP servers, AI gateway, and Unity catalog. This episode pushes that same habit across 15 more sprint-level calls. It's Monday at Data Dino, and the sprint board has 15 tickets waiting. Every one of them is a real architecture call, the kind that shapes how the museum chatbot, the licensing pipeline, and the curator tools actually run. RAG or agent, standard or storage optimized endpoint. Log the new agent as PyFunk or as chat agent. Does PII masking stored at ingest or at the gateway? Do we reach for the groundedness scorer or write custom code? The senior architect doesn't agonize over any of these. She reads the ticket, eliminates what won't work, and decides. Here's the pattern in one sentence. Read the last sentence of the scenario first, because that's where the binding constraint hides. Eliminate every option that violates that constraint. Then, among the survivors, prefer the Databricks-native primitive over rolling your own. That's it. The reason this works is that the last sentence is almost always a qualifier, fine-tuned, sub 200 milliseconds, cross-workspace, 1 billion vectors, and that qualifier is what makes one option correct and the others merely plausible. Think of it the way a doctor reads a chart. They don't start with the patient's name. They scan vitals and chief complaint first, because that's the diagnosis shaping signal. In our scenarios, the last sentence is the chief complaint. Phrases like fine-tuned model, sustained 800 queries per second, or cross-workspace sharing, those are vitals. Everything before it is patient history, useful for context, not for the diagnosis. The most common way good engineers ship the wrong architecture is by optimizing for the first sentence instead of the last. Each scenario follows the same 3-beat shape. First, the scenario itself, the ticket as it lands on the sprint board. Then the elimination, where we walk through why each tempting wrong answer fails in production, not just on paper. And finally the call, with a one-line rationale you can carry into your own designs. 15 scenarios across 6 architectural domains, each reflecting a real sprint-level call. Here's the distribution. Application development gets 5 scenarios. The largest slice, covering chain composition, agent base class, MCP integration, MLflow log flavor, and Unity catalog registration. Design applications gets 3. The architecture shape calls. Assembling and deploying takes 3 more. Serving mode, gateway placement, inference tables. Data preparation gets 2. Chunking and embedding choice. Evaluation and monitoring gets 1 focused scenario on scorer selection. And governance closes with the agent rule of 2. Together, these 6 domains cover the full architectural surface area. Scenario 1. Data Dino's curator team wants an exhibit blurb generator. The flow is simple. Pull species facts from the vector index, then write a 200-word visitor description. 2 clearly defined steps: no branching, no live tool calls, no judgment about ordering. The team's first instinct is to reach for an agent because, quote, it should be able to pick the right approach. And here's the last sentence of the ticket. The steps are fixed and known in advance. Walk through the eliminations. A standalone LLM call drops out immediately, without retrieval. The model invents extinction dates, which is exactly the failure mode we hit in episode 4. An agent with autonomous tool selection sounds appealing, but it wastes a planning step on a pipeline whose order is already fixed. A multi-agent supervisor is even further off. That's 3 agents for a problem that has 2 steps. The right call is a deterministic chain: retrieve, then prompt template, then chat Databricks, then output parser, LCEL pipe composition, one file, traceable end-to-end. If branching emerges later, we can promote it to an agent then. Scenario 1. The call. Fixed steps in a known order means a chain, not an agent. Every additional tool call adds latency, adds cost, and adds another place the pipeline can fail. You only earn the agent shape when something downstream actually requires runtime planning. Scenario 2. Data.Dino is authoring a new research agent. Multi-turn conversation, streamed tokens, tool calls into both the Museum Knowledge Index and an external partner API. The team has to pick a base class. 3 real options on the table: subclass Python model directly, use chat agent, or use ResponsesAgent. There's also some legacy chat model code in another repo, and one engineer wants to reuse it. The last sentence is the qualifier. This is new code being written in 2026. Eliminations. Subclassing Python model directly works mechanically, but you give up streaming, auto-inferred signature, and AI gateway inference table integration. Chat model is deprecated in MLflow 3, with a hard sunset for new code. That's the vendor position, not an opinion. A hand-rolled HTTP server duplicates everything the framework already gives you for free. The right choice for new code is ResponsesAgent. It's the current canonical class, wire-compatible with the Responses API, supports Pydantic v2, annotations, custom inputs and outputs, and MLflow auto-infers the signature. Chat agent is acceptable only for code that's already on it. Scenario 2. The call. For any new agent in MLflow 3, ResponsesAgent is the canonical base class. Chat model is deprecated. If a question gives you both options and the date is 2026, ResponsesAgent wins by vendor policy alone. Scenario 3. Data.Dino's research agent needs to query a partner museum's licensed REST API, gated by a bearer token. One engineer proposes the quickest path: hard-code the token in a notebook config cell and ship it. Security review will block that within 24 hours. But let's pretend for a moment they don't. The last sentence is the constraint that actually matters. Credentials must never appear in agent code, MLflow artifacts, or trace logs. Eliminations. Hard coding leaks the token to the MLflow artifact and any trace that captures the call. An environment variable on the serving endpoint avoids the artifact, but gives you no audit trail, no rotation, no Unity catalog governance. Standing up a custom MCP server just to wrap one REST call is overkill when external MCP already handles this pattern. The right placement is an external MCP server with a Unity catalog HTTP connection holding the bearer token. Because the partner bills per workspace, shared principal authentication fits. One identity represents every caller. The token lives in the connection, never in the agent. Scenario 3. The call. A third-party API with a single workspace credential maps to external MCP plus a Unity catalog HTTP connection. Not a literal encode, not an environment variable, not a custom server. This is the exact pattern Data.Dino landed on in episode 13, and the reasoning hasn't changed. Quick checkpoint. 3 scenarios down. Chain versus agent. ResponsesAgent versus the alternatives. External MCP versus a hard-coded literal. Notice the same shape each time. The last sentence held the constraint, and the constraint did the eliminating. Next, we're going to walk through how that agent gets logged, and then how it gets registered. Scenario 4. The agent is written, tested locally, and now it needs to be logged for serving. 3 flavors are on the table: MLflow.pyfunc.logModel, MLflow.langchain.logModel, or the agent-specific log call from Databricks agents. One engineer reaches for Pyfunc because, in his words, it works for everything. The last sentence is the qualifier. This is a conversational agent that needs streaming, tracing, and AI gateway inference tables straight from the Databricks docs on authoring agents. The platform leverages MLflow's chat-style base classes specifically to guarantee compatibility with evaluation, tracing, deployment, AI gateway, and streaming output. The takeaway here is plain. Generic Pyfunc doesn't carry those integrations. If you log a chat-style agent as generic Pyfunc, the platform doesn't recognize it as an agent, and you forfeit every one of those features. Think of it as a generic shipping box versus a labeled, bar-coded one. Log as generic Pyfunc and you lose streaming token output, you lose auto-inferred signatures, you lose AI gateway inference table integration, and you lose the MLflow tracing hooks that emit agent spans automatically. Log through the agent flavor and you keep native ResponsesAgent serialization. You can declare the resources list, so model serving auto grants the vector index and foundation model endpoint, and streaming, tracing, evaluation, and inference tables all wire in without extra code. Scenario 4. The call. A conversational agent gets logged through the agent flavor, not as generic Pyfunc. The specialized class keeps every integration you'd otherwise have to rebuild by hand. Datadino's pure LCEL chain from episode 12 uses the LangChain flavor for the same reason. Match the flavor to the shape of the thing you're logging. Scenario 5. Datadino needs to share the museum agent with a partner workspace at a sister institution, and the audit requirement says lineage must trace from the source delta tables all the way to the registered model. The old habit at the company is the workspace registry. It's familiar. The team knows the UI. The last sentence is the deciding qualifier: cross-workspace sharing with end-to-end lineage. Direct from the lifecycle documentation. Models in Unity Catalog extends Unity Catalog's benefits to ML models, including centralized access control, auditing, lineage, and model discovery across workspaces. Notice the words centralized, across workspaces. Those are exactly the 2 requirements the ticket put on the table. The workspace registry simply doesn't have those properties. Side by side, the workspace registry gives you all or nothing permissions inside one workspace, no real cross-workspace sharing without manual copies, deprecated stage names like staging and production, and no automatic lineage back to source tables. Unity Catalog gives you the 3-level name, catalog.schema.model, mutable aliases like champion and challenger, automatic lineage from MLflow.loginput through to the serving endpoint, and the default registry URI is now Databricks UC. New MLflow 3 code lands in UC without any explicit configuration. Scenario 5. The call. Cross-workspace sharing, lineage requirements, or governed access, any of those words in the ticket point to Unity Catalog with the 3-level name. Datadino registers under prod.fossilrag.fossilchatbot, and that's the same shape every governed model lands in. 5 scenarios in, and application development is closed. Chain versus agent, ResponsesAgent versus the alternatives, external MCP, the agent log flavor, and Unity Catalog registration. Notice the through line. Every binding constraint came from the last sentence of the ticket. Next up is design applications, where we make the architecture shape decisions that set up everything downstream. These 3 calls determine whether the rest of the build is fighting upstream choices or coasting on them. Scenario 6. product wants a question and answer app over recent stock news. Engineering's first proposal is RAG over a vector store of articles. Marketing pitches something simpler. Just use a big foundation model with a long prompt. Both are wrong, but for different reasons. The last sentence of the ticket settles it. Questions include current stock prices. Walk the spectrum left to right. A standalone LLM call only knows what was in its training data. No live prices, no fresh articles. So that's out. RAG adds semantic retrieval from the article corpus, which solves the article's half of the problem, but RAG can't fetch a live stock price. That's out too, at least as a complete solution. An agent combines both. It can retrieve from the article index as one tool, and call a market data API as another. The live prices requirement is the constraint that decides it. The right shape is an agent, with RAG serving as one of its tools. Scenario 6. The call. Whenever the question itself contains real-time data, current prices, current weather, current inventory, that's an agent. RAG handles the static document side as one of the agent's tools, but the live side needs an actual tool call to a fresh source. Scenario 7. Data Dino has 2 vector workloads landing in the same sprint. The licensing partner has 1.3 billion archive chunks and tolerates 400 milliseconds of retrieval latency. The museum chatbot, the one we sized in episode 8, runs at 80 queries per second with a sub-200 millisecond latency budget. Procurement asks the natural question: can we use one endpoint shape for both? 2 constraints, 2 different shapes. From the Vector Search Performance Guide, choose storage-optimized endpoints when you're working with 10 million or more vectors, can tolerate some extra latency, and need better cost efficiency per vector, up to 7 times cheaper. 3 conditions, all of which must apply. The archival workload satisfies all 3. The chatbot satisfies the first one and fails the second. The shapes are clear. Standard endpoints handle up to roughly 320 million vectors at dimension 768, deliver sub-200 millisecond retrieval, support both continuous and triggered sync, and that's where the live museum chatbot belongs. Storage-optimized endpoints support triggered sync only and cost about 7 times less per vector. They scale past 1 billion vectors per endpoint, and they carry roughly a 250 millisecond latency floor. The licensing archive belongs there. The latency floor is what disqualifies storage optimized for the chatbot. The contractual budget is 200 milliseconds, and the floor alone exceeds it. Scenario 7. The call. 2 endpoints, not 1. Standard for the latency-bound chatbot, storage optimized for the billion vector archive. The latency floor is the line that decides anything below it can't run on the freight train, no matter how cheap the storage is. Scenario 8. Data Dino's Fortune 500 contract has accuracy thresholds written into it, and they cover both retrieval and generation. The engineer who built the pilot suggests reporting cosine similarity between the chatbot's answer and a reference answer, which, as we saw in episode 18, collapses the first time a client looks closely. The deeper issue is that when accuracy slips, client legal will ask which leg of RAG is failing. The last sentence says it plainly. The SOC2 auditor needs per-component diagnostic scores. Walk the eliminations. A single cosine score is opaque. When it drops, you don't know whether retrieval found the wrong documents or the generator drifted. Output BLEU alone is blind to hallucination. Final answer accuracy alone is silent on retrieval. The right evaluation is the RAG-evil triad: retrieval relevance, retrieval groundedness, and relevance to query, paired with correctness and retrieval sufficiency using the expectations field for labeled facts. Run all of it through MLflow.GenAI.evaluate on a labeled golden set. Per-component scores are what survive the auditor's questions, because each one points at a different leg of the pipeline. Scenario 8. The call. Component-level evaluation with the RAG-evil triad. One score can never tell a client whether retrieval or generation broke. Datadino's diagnostic split in episode 18, 94% groundedness, 76% sufficiency, pointed straight at retrieval recall as the real problem. That diagnosis is only possible if you score the legs separately. 8 scenarios in architecture shape, endpoint shape, evil shape, design applications is closed. Notice the pattern still holds. The last sentence picked the answer each time. Next we're on the deployment plane, serving mode, gateway placement, and inference tables. Then data preparation, the evaluation scorer call, and we close on governance. Scenario 9. Datadino's fossil chatbot ran on pay-per-token through the pilot, bursty, low volume, no compliance concerns, perfect fit. Now the workload has changed. Sustained 80 queries per second, a contractual sub-200 millisecond 95th percentile latency target, and a fine-tuned exhibit blurb adapter sitting on top of the base model. Finance asks whether pay-per-token can carry this with some rate limit headroom. The last sentence is the qualifier: fine-tuned, sustained, contractual SLA. The Foundation Model API documentation is explicit on this. Provisioned throughput is the recommended path for all production workloads, and especially the ones with high throughput needs, performance guarantees, fine-tuned models, or additional security requirements. Datadino's ticket hits 3 of those 4. That ends the debate before the cost conversation even starts. Side by side, pay-per-token runs on shared capacity, so it cannot promise a 95th percentile guarantee. It's rate-limited per principle. It's the right choice for prototypes and bursty internal tools, exactly where Datadino started, and it carries no SLA guarantees for fine-tuned models. Provisioned throughput allocates dedicated capacity with a consistent 95th percentile latency, is required whenever you need performance guarantees on fine-tuned or custom models in production, is required whenever an SLA is contractual, and is the right choice for sustained production traffic. The decision is made by the constraint, not by which one is cheaper this month. Scenario 9. The call, fine-tuned weights or a contractual latency SLA flip serving to provisioned throughput automatically. The constraint makes the decision, not the cost preference. If finance wants to optimize spend, that conversation happens within provisioned throughput sizing, not by trying to keep the workload on pay per token. Scenario 10. Curator records contain visitor email addresses, and some queries pull those into context. 3 engineers, 3 proposals, mask inside the chain, mask at ingest, before the data ever lands, or mask centrally at AI gateway. The complication: the chatbot is one of 4 endpoints that touch curator data, and the last sentence makes the policy requirement explicit. Every endpoint must apply identical PII policy. The Unity AI Gateway documentation makes this point directly. Beyond routing and rate limits, the gateway provides guardrails like PII detection, automatically blocking or redacting sensitive data wherever it appears in the inputs or outputs of a model. That word, wherever, is the whole point. The gateway sees every request to every endpoint behind it, so one policy applied there enforces uniformly across all 4 endpoints in Datadino's case. Think of it as airport security. You don't put screening at each gate. You centralize it at the terminal entrance, where every passenger has to pass through. In our case, the 4 endpoints on the left, chatbot, summarizer, research agent, and internal tools, all route through one AI gateway in the middle. The gateway runs PII redaction, applies rate limits, and writes audit records. Then traffic continues to model serving on the right. One policy, applied wherever PII appears in inputs or outputs, governing every endpoint behind it. Scenario 10. The call, PII masking belongs at AI gateway, not buried inside each chain. One policy, enforced uniformly on every endpoint that crosses the gateway. Inside the chain, masking forces every team to remember to implement it. Gateway masking removes that risk from the application layer entirely. Scenario 11. 3 internal teams at Data share one model serving endpoint, and finance wants per team chargeback. Separately, the SOC2 auditor wants the full request trail, token counts, latencies, everything. One engineer proposes writing a Python middleware that logs to a custom delta table, reasonable instinct, but the last sentence narrows it. 0 application code change, and the audit log must be queryable directly in SQL. Eliminations. Hand-rolled middleware fails the 0 code change constraint immediately. Every team has to adopt it and keep it updated. App-level logging bypasses Unity catalog governance entirely. MLflow tracing is excellent for debugging individual requests, but it isn't built for billing rollups across millions of calls. The right path uses AI gateway inference tables. They capture every request with no client code change. Attach a usage context map for tenant attribution. Join system.serving.endpoint usage for the chargeback math. Then attach an inference log monitor on top to produce the SOC2 dashboard automatically. That's exactly what Data wired up in episode 19. Scenario 11. The call. Inference tables plus usage context give you chargeback and audit with 0 application changes. That's the Databricks-native answer. Whenever you see 0 code requirements paired with audit and cost attribution, this is the pattern. 11 scenarios in serving mode, gateway placement, inference tables, assembling and deploying is closed. The through line keeps showing up. The Databricks plane already has the right primitive. The work is recognizing which one. Next we move to data preparation, where most RAG quality is actually won or lost. Chunking and embedding choice, 2 scenarios. Scenario 12. Data's licensing team needs RAG over 200-page contracts, and the contracts use multi-column layouts. The first pass used pipedtf as the loader and 500 token fixed chunks with no overlap. Recall measured 32%. Clauses split mid-sentence, headings detached from their sections, and the retriever couldn't find clean clauses to return. The last sentence is the constraint. Clause-level context must survive into retrieval. 2 columns. On the left, what broke it? pipedtf on multi-column legal PDFs jumbles the reading order. Text from column 2 interleaves with column 1. 500 token fixed chunks chop clauses in half, and without section header prefix, semantically similar clauses from different sections become indistinguishable in the vector space. On the right setup. Prepend the section header path to every chunk. Use iParse document for layout-aware extraction. Switch to a recursive character splitter at 1500 to 2000 tokens with meaningful overlap, and use iPrepSearch, currently in beta, to enrich each chunk with titles and page references. Scenario 12. The call. Complex layout means iParse document. Clause integrity means larger chunks, real overlap, and section header prefix. Parsing and chunking fix recall before any model change can. Garbage in, garbage out, and on multi-column PDFs, pipedtf is the garbage step. Scenario 13. 3 corpora land in the same sprint. Short visitor FAQs, 1500 token legal clauses from Scenario 12, and multilingual partner pages from European institutions. One engineer wants to standardize on a single embedding model for simplicity. The catch: the standard BGE models have a 512 token window, GTE has 8192, and Qwen3 embedding has 32,000 tokens plus over 100 languages. The last sentence locks the rule. Chunk size must fit inside the embedding context window. The wrong move is one size for everything. Use BGE across all 3 and it silently truncates the 1500 token clauses at 512, No error, no warning, just degraded recall. We watched Data Dino make exactly that mistake in episode 7. Reach for the Databricks GTE large English endpoint for all three, and the multilingual partner pages fail. That specific endpoint is English only, even though the broader GTE family does have multilingual variants. Use the largest model for all and you pay for context window you never use. The right move matches the corpus to the model. The multilingual partner pages need Qwen 3 at 32,000 with multi-language support. Long legal clauses need GTE at 8,192. The non-negotiable rule, chunk size never exceeds embedding context, ever, and short FAQs run fine on BGE or GTE. Scenario 13. The call. Match the embedding window to your chunk size and your language need. Silent truncation past the window is the most expensive bug in RAG. Precisely because there's no error message, the pipeline runs green while recall craters. Scenario 14. Each failure mode has a different diagnosis, and that means a different scorer. 3 failure modes arrived in the same week. The museum chatbot fabricated a Triceratops extinction date, a hallucination. The summarizer leaked a visitor email address into an output, and the Genie tool produced an incorrect SQL query that ran successfully but returned the wrong rows. The PM asks the natural question, should we just add every built-in scorer and call it done? The last sentence narrows the requirement. Production monitoring must catch each failure mode specifically. Walk the mapping. The hallucinated extinction date is a grounding failure, so retrieval groundedness is the diagnostic. The leaked email is a safety and PII issue. Safety judge plus an @scorer regex catches it. Wrong SQL is a correctness problem you only catch by executing the query. So write a custom @scorer that runs it and diffs the result. Off-topic drift gets a guidelines judge with a domain rubric. Pick the scorer that matches the failure mode, not all of them at once. Scenario 14. The call. Diagnose the failure mode first, then pick the scorer that matches it. And one operational detail worth remembering, only @scorer decorated functions defined in notebooks can be promoted to scheduled production monitoring. Class-based subclasses run in offline evaluation only. Scenario 15. The HR team proposes an agent that answers benefits questions and updates PTO balances directly. Look at the 3 properties this agent holds. Inputs are free-form employee chat, that's untrusted text. Data is the employee record set with social security numbers, salary, and benefits, that's sensitive. Actions write PTO updates to the system of record, that's consequential. The prototype passed every functional test. Security review is next, and the last sentence is the trigger we need to act on. The agent rule of 2 from episode 17 frames this exactly. 3 pillars, all present at once. Untrusted input at the top, the free-form employee chat. Sensitive data at the bottom left, social security numbers, salary, benefits. Consequential action at the bottom right, the agent writes PTO balances. When all 3 sit inside one agent session, you have the lethal trifecta. A prompt injection payload embedded in employee text can instruct the agent to read sensitive records and write an unauthorized PTO change in the same turn. The blast radius is full breach. Left column is the prototype as proposed. Untrusted input flows directly to retrieval. The agent reads social security numbers and salaries with no mediation. The agent writes PTO balances without a checkpoint. Any successful prompt injection causes full breach. Right column shows the fixes. Any one of them is enough. Gate PTO writes behind a human approval tool, so the action requires explicit sign-off. Or split the architecture, a read-only agent that answers benefits questions, and a separate write workflow that doesn't see free-form input. Or strip sensitive fields at ingest with Unity catalog column masks, so the agent never sees them. Any single one of these drops a pillar, and the triangle collapses. Scenario 15. The call. An agent that holds all three pillars must drop one. Gating the consequential action behind human approval is the most common fix, because it preserves the user experience for read queries while removing the autonomous write capability that creates the breach risk. Count the pillars first. If you get to 3, break the triangle. Same pattern, 15 times. Read the last sentence first to find the binding constraint. Eliminate the options that violate that constraint. Among the survivors, prefer the Databricks-native primitive over rolling your own. And then verify, confirm the choice respects the other constraints carried through the scenario, not just the headline one. 4 steps, every decision, every time. All 15 calls condensed. The constraint sentence is on the left. The right call is on the right. Pause on this if you want a single sheet to carry into your own sprint planning. Notice that no 2 calls are identical, but every one of them was made by reading for the constraint first. That's the cheat sheet behind the cheat sheet. 4 things to carry into every build. The constraint sentence is the diagnosis. Read it first, before you look at the option list. Among technically correct options, the Databricks-native primitive almost always wins, because the platform already wired the integrations you'd otherwise reinvent. Specialized classes like ResponsesAgent and ChatAgent keep streaming, tracing, signatures, and gateway hooks that generic PyFunk gives up. And governance, masking, audit, lineage, rate limits, lives on the gateway and in Unity catalog, never inside chain code. Senior engineering, in the end, is recognizing the constraint that decides the call. 15 scenarios, 1 habit. The same instinct that makes a good architecture review also makes a good scenario answer. Read for the qualifier, eliminate what won't survive it, prefer the platform primitive. Carry that into the next sprint, and the calls start making themselves. That's it for Senior Engineer Walkthrough. 15 real-world scenarios. Drop a like if this clarified things, subscribe so you don't miss the rest of the Databricks GenAI Engineer Cert, and I'll catch you in the next video.